Okay. Uh, Hello. This is the homework 4 for Module 5 Physics, Advanced Mechanics. It is on motion gravitational field part 2. Let's get into multiple choice. So the first question, planet A with a diameter d and mass m has a gravitational acceleration at the surface equals to 5 meters per second squared. Planet B has a twice of its diameter and an 8 times its mass. Okay. So this question pretty much just plays around with the gravitational field strength equation. If you might recall, it equals to that. And oh, okay. So Gm over r squared. Okay. And then you try to relate this with planet A and planet B. And therefore, you can use these two equations, okay, and then you get some sort of relationship. But the quickest way to do this is you can divide two equations. In that way, you can quickly get a ratio of Gn and Gb. Um, yeah, and that's calculating it. Okay, so the answer is C. Question two. A satellite is in a stable circular orbit around Earth with a velocity of orbital velocity. Okay, quick. So the satellite escape velocity in this case. Okay, so if you're paying attention in class, you should know that our escape velocity is square root of 2 gm over r, while the orbital velocity is equals to square root of gm over r. And as you can see from the relationship, the escape velocity is exactly square root of 2 multiplied by the orbital velocity. Therefore, and that number is 1.414 or something, yeah? So it's B. Okay. Question three. 5,000 kilogram satellite is in stable circular orbit with a radius of 7.5 times 10 to the power of 6 meters around Earth. What is the gravitational potential energy of this satellite? Um, okay, so like simply use the equation over R. Okay. All right, so next question. Mars has two moons, Phobos and Deimos, okay, which are in near circular orbits. The ratio of the orbital radius this. Okay, so like if you ever see questions asking about radius, like ratio of I don't know, radius and period, it's almost like most likely it's gonna be like a Kepler's law question. Okay, supply Kepler's third law, should be able to get the ratio. Okay, just make sure to keep track of the powers. Question five, a space capsule is moved from point P to point Q. Which of the following rows of the table is correct according to the space capsule? So from P to Q, you have increased your altitude. Work done must be positive, okay? Because like there's an increase of total energy. Also, gravitational potential energy also increases because, like we discussed in class, potential energy monotonically increases with radius. Okay. All right, so question six. Rocket is launched from the surface of Earth. Its gravitational potential energy and kinetic energy will change. A rocket's engine are turned on to apply a continuous thrust. Which of the following graphs best show changing rockets' gravitational potential? Uh, so potential energy must increase. It has a relationship with R. Kinetic energy from the surface. Okay. So the following graph best shows the changing of its gravitational potential and kinetic K. Yeah, pretty much that, right? So like K increases and potential also decreases. Okay. It's just like I was thinking that because kinetic energy doesn't necessarily increases like this. It could be increasing like another means like something like this, right? Or like that. This is just like a particular curve that shows it's increasing. Okay, that's pretty good. Question seven, which of the following rows of the table provides the best comparison between satellites in low Earth orbit and geostationary? Low Earth orbit has lower altitude. Okay, and geostationary has a higher altitude, and because of the orbital speed equation, it's I'm just gonna remind you, V is equal to square root of gm over r. So we have a larger radius at geostationary orbit, so that means a smaller speed. Okay. Okay, so International Space Station (ISS) is in a circular orbit 400 kilometers above Earth's surface. Mass is that, which of the following is correct? So the ISS needs occasional boosting. Yeah, because it's in a low Earth orbit and you have orbital decay happening. So yeah, A is the choice. Question 9, the orbital speed of ISS at this altitude is closest to. Yeah, you just use the orbital speed equation. Okay. Question 10 is also a C. Okay, that satellite is in a uniform circular orbit around Saturn and completes one revolution. Okay, mass of Saturn. So you just use Kepler's third law, which relates the mass of the host planet that's being orbited. Yeah, and then pretty much from there. Okay. Extended response. Let me just check if I recorded the session. Yes, I did. Okay. Um, so extended response. A 200-kilogram satellite. 200-kilogram satellite is in a stable circular orbit at an altitude of 300 kilometers above Earth's surface. Calculate the gravitational potential energy of the satellite at this altitude. Pretty much just a direct substitution of equation. Okay. So make sure to keep track of your powers. It's very easy to forget them. And don't forget, it's given an altitude. So that's not the orbital radius. Inside the equation, this is orbital radius. So you must add up Earth's radius. If you haven't remembered it, it's 6.371 times 10 to the power of 6 meters. Question B, calculate the satellite. The satellite is then moved to a new orbit. Okay, so it's from orbit to orbit. That means like we have to calculate the work done with its changing total energy, because not only we have to change the altitude, we also have to supply this the required kinetic energy for it to maintain. Okay, so yeah, just use the net total energy equation. Although I should have also derived the total energy like formula, GMM over 2R, in this case, but like I think you guys know how to derive it, so just leave it to be. Question C, the actual work done on the satellite is greater than the theoretical value calculated in part B. Yeah, so I suggest one reason. So the rocket would experience a very significant aerodynamic drag, right? When it's launched from Earth, right? Um, yeah, and which does negative work on the rocket, so that means you have to supply excess work, okay, to counter this, okay. Right, and there's always also the efficiency of the engine and stuff. It never is 100%, okay. Question 12. Describe the concept of escape velocity and show that it's that. Okay. So the concept of escape velocity is defined as the minimum speed for a satellite to escape a certain gravitational field. Escape meaning that its total energy goes to zero. Okay, so before it's escaping, the total energy is less than zero. Escape means that the total energy is greater or equal to zero. At the point where you just about to escape, total energy is zero. You can use this fact and definition of total energy is U plus K, rearrange for your velocity to derive for the escape velocity. Question B, substitution of values. Okay, should be fine. Question C, compare the concept of escape velocity with orbital velocity. So this question, I particularly make annotations on how to get marks on this one. Okay, so yeah. So yeah, these are similar and like also different concepts. Okay, so like make sure to also include similarity and differences because of the compare question. Even though it's not like a big compare, but it should also give like similarity and differences simultaneously. Also define them. Okay, it's very important to get that extra mark. Okay, so pretty much have a read. This is pretty easy question. Question 13. Outline the experiments for a satellite to maintain a geostationary orbit around Earth. Your answer should include calculations of the orbital radius and three other requirements. Okay. Yeah, so maintain a geostationary orbit around Earth. Okay. So what I said is basically calculate a bunch of like radius, like because that's the radius you have to achieve, right? So and then there's also the altitude as well. Right. So like I did for the radius, but you guys can do like something else, right? So any calculation calculate for the speed, like the speed that's required. Yeah, that also is a requirement as well. Okay, so yeah, using Kepler's law to calculate the radius, and then like this need is that we have to go to this precise altitude, and we need to have a circular orbit with a centripetal force applied by the gravity. Okay, must be directly above Earth's equator. Yeah, yeah, that's another requirement. So geostationary satellite is by definition relatively stationary to Earth's rotation, so it has to be on the um above the equator for it to be relatively stationary. Okay. Um, yeah, and also you have to move in the direction where Earth is rotating. So yeah, that's the last one. Question B, justify one of low Earth satellites and one use of the geostationary satellite. Yeah, so International Space Station is like one of the use of low Earth orbit. It is in lower altitude because you can like people can go on, can get off, right? It's like, make transportation very easy because it's closer. And because of it's also closer, that means the communication delay is very short. So it could also be used in communications as well. And geostationary satellites are typically used for also communications, but like because it's always above one point on Earth, it's almost like focused. It's very good use for like a local communication and broadcasting and stuff. Okay, so I just basically see anything that makes sense in terms of their like orbital characteristics should be fine. Okay. And then we have question 14. Pretty much just algebraic expressions. And if you just do algebra correctly, you should be able to verify this statement. Okay, it's very nice intrinsic relationship between all the energies of satellites that's undergoing uniform circular motion. So yeah, keep in mind this is only true in uniform circular motion. Okay. Yeah, the next one is just plotting the graph. It should be quite trivial. Okay. Uh, yeah. So question 15, the orbit of a comet is as shown, it's like a highly elliptical orbit. Okay. Relate the comet's orbit in one of Kepler's planetary motion. Okay, so basically first law, right? It's very elliptical. That's what Kepler said. And the question B, sorry, give me a sec. Question B, explain the changes in the comet's energy as it completes one orbit from point P. Okay, so as it gets closer and it gets further away, okay, so initially the comet moves towards the perigee, which is the closest distance of the ellipse from the focus. Okay, as a result, potential energy is converted into kinetic, so it gets faster, or it slows down, right? It gets faster, but its potential decreases. Okay, at the opposite side of P, the perigee, okay, the comet is um sorry, did I wrote perigee? Okay, That's the opposite side of P. This side, it's the it's the parity. The comet is closest to the sun, hence potential energy is minimum, kinetic energy is maximum. Also, as the comet continues from parity, it moves to the apogee, and at that point you have it goes back to the apogee, and at that point you have a larger potential and smaller kinetic. It is transfer between potential and kinetic while keeping the total mechanical energy invariant. Okay. So just make sure you also say that, like the invariant of total energy. Question 16. So International Space Station, this much, the ISS is in low Earth orbit with an altitude of 405, bunch of orbital parameters. Okay. So calculate the orbital period. Okay, that's just Kepler's law. Right, B is like explain why orbital decay. Okay, that's explaining orbital decay. So you want to define it first. Orbital decay is a phenomenon where atmospheric drag reduces the speed of satellite such that the required centripetal force becomes larger than the required, so it goes back in, spirals in, right? So like we have to boost it up, right? So this is a change of orbit. So we have to calculate the total energy change. Okay. And then question 16D, the energy is provided by two engines located on the Russian module. Okay. calculate just how much you're gonna pay for that. Okay, so it's like tells you each kilogram the fuel costs this much. Calculate total like cost for this maneuver to happen. I think I misspelled. I misspelled maneuver. This should be maneuver instead of maneuvers. Okay, but like it is what it is. So the mass of all the thing that we're gonna use is this much. Okay, then calculate the cost by times it by the cost for each kilogram. So it's quite expensive. Every time you have to boost it. Okay. Question 17. This question is very interesting because it looks at the one of the experimental evidence that suggests inside our galaxy, like the center of the Milky Way galaxy, there exists a super giant black hole. It's called Sagittarius A. Sagittarius A star, okay, because it's like a center object. We don't see black holes because they don't really emit light like the sun, like any stars. They are pretty much just black, okay, despite they have equation disk, but it's very like dim. Okay. The way we detect this black hole, we confirm the existence of this black hole is through the orbital motion of nearby stars. Okay, and then using that and from Kepler's law, we are able to calculate its mass and end up finding that it's very huge. So it satisfies the hypothesis made by Einstein that it has to be a bizarre object, something like a black hole. Okay, so black hole has a very enormous gravity, too large, so large that light cannot be even escaping. It attracts light. Okay, so that's why it's also dark. So yeah, so with the information provided, calculate the mass of Sagittarius A. Okay, like bunch of um periods and stuff are being given. Okay, so use Kepler's law. Okay, so be careful that although like these orbiting objects are elliptical, highly elliptical, but Kepler's third law is still in application because in general, like r cubed divided by t squared, r cubed is actually a radius. It's actually not only radius, it's also the semi-major axis for elliptic orbits. Okay. Yeah, so you can use that to calculate it. Indeed, it's very huge. As in comparison, our sun only has a mass of 10 to the power of 30. Okay. So that's like 10 to the power of 10 times larger. Okay. That's huge. Question 17, continued. Yeah, so it's asking us to calculate something called the Schwarzschild radius, which is basically the radius of the event horizon, which is basically the effective radius of the black hole itself. Right? This is the radius where light cannot escape. Okay, so what we're supposed to do is we're supposed to calculate the escape velocity here. The escape velocity is equal to speed of light, which is 3 times 10 to the power of 8. Rearrange for that radius, you get the Schwarzschild radius. Okay, it is at that surface of a sphere of this Sagittarius radius of this Schwarzschild radius. Even if you travel at the speed of light, you can't escape that. But we can't travel at the speed of light, as we will see in Module 7. So this is pretty much why you can't like escape from a black hole. It's literally impossible. Okay. Yeah. So challenging question for this week is also pretty interesting as well. It looks at yeah, the picture on this black and white looks a bit weird, but like it looks like the observation of our like the stars in our galaxy, how it's orbiting the central black hole, right? And then we end up finding that the orbital motion, the orbital velocity seems a bit weird. Okay, like using Kepler's law, we're expecting something like this to happen. But what we actually see something like this to happen. So Kepler's law is somehow not obeyed by those objects. Okay, so what does this mean? Is like somehow the outer layer of the stars in our galaxy are orbiting much faster than what we expect, right, from Kepler's law. So that indicates something weird because the scientist looks into it and we really can't find anything that explains this because using Kepler's law, like the gravity just tells us it has to be moving at a smaller velocity. However, so with Kepler's with our observation, this shows that it almost looks like that the galaxy is holding more mass than we expect it to be. Okay, so using Kepler's law, calculate the expectation of orbital speed. of a star located at the edge of galaxy. Yeah, so that's what we did. We calculated, okay, using Kepler's law. Calculate the period as well. Okay. Um, given that the observed orbital speed is this much, so it's like way smaller. Okay, way smaller than expected. Okay. So and then if it is if it is moving not smaller, way faster than what's expected. So if it is moving at the speed, then what is the required mass that this object must be like attracted with in order to get this much orbital speed to happen? So just reverse engineer your equation to get the orbital speed and then rearrange for the mass. You get we need this much mass. Okay. So but our galaxy only has mass of like 5.0 times 10 to the power 10 mass of our sun. Okay, so that's the problem. Like we only see this much star, we are expecting this much mass, but the actual mass required for our observation for these orbital speeds are much higher. Okay, so what that means is basically we have to account for these excess mass that we don't know what are they. Okay, and we just basically call them dark matter. All right, it's very dark because we don't see them; they're not visible, but they have gravitational attractions on planets and stars in our galaxy. Okay. Yeah, so that's like a big thing. So if you find evidence for dark matter, you find some interaction that dark matters obey, you should win a Nobel Prize for it. Okay, so yeah, it's actually very dominant as well. It's almost 71%. Okay. And question 20 looks at binary stars. Okay. So part A pretty much just calculates asks you to prove the Kepler-Star law version for binary, where R is like the distance between the stars. You can do this by calculating the net forces and then use centripetal force. So something to note is that when you equate the centripetal force equation, this RA is different to this R. See how this R is like the distance between two planets and RA is like to the center of mass. They revolve around the center of mass. If you just rearrange and then if you're very good at algebraic manipulations, you should end up with this equation. Okay, it's a very hard question, and these questions after question 20 are like actually hard, algebraically heavy. So yeah, just have a look at my working out, see if you guys have any question. You can ask me. Question B is use that equation, pretty much directly using it. Question C asks you to prove something like very not rigorous. Okay, so the trick here is that you have to manipulate the equation you had above, and you have to really manipulate them to get what you want. Okay, this is not a trivial result. It needs to be manipulated. Okay, so like have a look at the working out. So pretty much you can get this relationship of the radius from the equations above, right? This equation that we get from centripetal force and gravity with the v equals to 2 power over t substituted, and eventually you'll get this relationship, and then from that you can manipulate it, okay? Because r and stuff like you can get this relationship, right? Okay, and then question D, determine the orbital speed of VA and VB. Okay, well that's just I guess because you know about RA and RB, and then you can calculate RA and RB using this distance R, which is given using the equations above, and then using definition of velocity you can calculate it. Okay, so they have the same period but different velocity due to the circles are different sizes. Okay? And then the radius of the circles are like ratio of the radius is also equal to the ratio of the masses, so it's kind of good. Question 21 is one that's involving deriving the position of L2. I guess in the extension material, I have shown the derivation fully for L1, okay, which is the one in between, okay. L2 is also derived in a very similar manner, except you have to flip a sign somewhere, okay. So from Kepler's law, you can basically derive this equation. This equation you can also like if you have very good intuition, right? This is called the center of mass. It's just by definition like the spatial average of different like of multiple masses in a system, like what's the average mass, like which location it is, right? So it's almost like the position of each plus together divided by the total mass, right? But you can also prove this using Kepler's law. Yeah, so pretty much from this equation right here, right, you can get this relationship, right? You can get this relationship, and then the distance are changed into parameters that we define here, and then so R1 minus RCM, okay, is the distance from the for the blue star to the center, and then the other one is the other one, okay? And then if you rearrange, algebraically manipulate this, you should get something out, okay? Question 21. To prove something like this to prove that the location of L2, that radius at L2 is exactly given as this expression, the solution of this expression, okay? With R, with like big R equals to R1 minus R2. It's really quite difficult. Okay, so what you're supposed to do is you also need to consider the net force equation, and then make sure you use the omega version. It's like because omega is like I don't know, it's like the omega are the same. So Lagrange points they rotate in synchronous with the planets. Okay, so omega for the planets and for the for the satellite there are the same. Okay, right, and then use the results from previous, okay, and then substitute what omega is, use results from like equation one and part A, yeah, to justify a bunch of substitutions, and then pretty much just end up with this final answer algebraically, okay. But keep in mind that this equation is kind of difficult to solve by hand, so we probably need to use a calculator or like to find roots, you can use a computer for it, okay. Right, so it's a very nice practice with like algebra for this extension material, for this challenging questions. If you have done the challenging question and then if you've done it correctly, you must have spent a lot of time on it. You have my respect. And yeah, this is it for this week's physics homework. I'll see you next time. Enjoy physics.